Good afternoon. Thank you for...
We're starting.
Thank you for having me here. Now, the topic I'm going to talk about, I started it 40 years ago. That was the first thing I did. I started very humbly and testing of the Lorentz transformations, test theories of the special relativity, and it evolved. And nowadays I'm not going to give even a summary because it is so long from when I started to where I am here now, and I cannot start half-page or anything like that because I suspect that you will be familiar. Hence, I'm going to do the following. I'm going to challenge it, and I want you, okay, to decide what you want me to talk about. All right? So, I'll give, first of all, let me say this. 1900 to 1930, that was the golden age of modern theoretical physics. Special relativity, general relativity, quantum mechanics. Well, all of them were right, but not quite. Okay? Not quite. There was something, but I'm not going to start with the special relativity or quantum mechanics because in the case of general relativity, Einstein already said something is not quite right here with general relativity, and he postulated teleparallelism. He didn't have any success at all, even though he corresponded with Cartan, and Cartan gave him good tips, but he didn't listen. Okay, so he utterly failed. All right. What happened 1915 to 1930? Peter the story. 1915, general relativity. In the time now you study general relativity, you study the Lev-Chita connection. But there was not any Lev-Chita connection, any connection in 1915, because the first one is from 1917. There were the Christopher symbols, but one thing is the Christopher symbols, and another one is to have the Lev-Chita connection, which uses the Christopher symbols. But at that point, the Christopher symbols were playing only a metric role, not a final role. So, Einstein postulated the parallelism, and he thought that by cranking the machine, okay, the sausages will come there, the sausage beam, electrodynamics, again, general relativity, and something that would replace, hopefully, quantum mechanics. But if we postulate teleparallelism, that means that part of the structure is integrated. Part of the structure.
He's moving.
More specifically.
He's moving around too much.
Sorry. More specifically, what it means is that we can speak of equality of vectors at a distance, independent of the path. So automatically, that implies a preferred frame. Einstein didn't realize it. Therefore, there is room for a preferred frame. He may have found incompatibility with the special relativity. But what happens? The special relativity implies the Lorentz transformation, but the Lorentz transformations do not imply a special relativity, and there are alternatives. I'll talk to you about two alternatives if I have time, of which I will speak only one interests me, and in addition, when I reach quantum mechanics, because I'm going to reach quantum mechanics, then you will see that the one which looks more separated from, more further apart from special relativity is the best one, even though the Lorentz transformations, still have a role to play. Okay, so, what's the point? No point. All right, don't worry.
Yeah.
Teleparallelism. Thank you. Now, teach me how to. So I push the green button.
Yes.
Yeah. So I already said that preferred frame field. Einstein also assumed logical homogeneity. Logical homogeneity, he said, of theoretical physics and differential geometry. Except that he didn't know how to use it properly. Because if it is logical homogeneity, what is fundamental in geometry? The equations of the structure. What is fundamental in physics? The field equations. So what he should have done is identify the two.
beginning of the picture.
Okay, as I said, at some point, I'll interrupt it. I won't have time to go to the bottom. If you wish, you go to the bottom. But I would like to try something else. Since there is going to be so much, okay, I ask you to tell me at some point, okay, interrupt me. Okay. So Einstein had this idea, logical homogeneity of theoretical physics and differential geometry. So this is what we are going to do. Then what happens is that with those two arrows take us to the geometrization of classical physics. I have put one more arrow, this one. Lorentz transformations. I already talked about the three options. The Schrödinger, I don't speak of him because of the Schrödinger cat or the Schrödinger equation, simply because he tried to geometrize the equation of motion of special relativity with Lorentz force. And he didn't achieve it. I didn't read his paper, I didn't need. What happens is that when I was able to geometrize it, then somebody else had already apparently done it, but I was first. Anyway, so the solution that we gave was provisional. Okay, say Riemannian plus torsion. But that is not sufficient. It is not possible with that differential geometry to do the matching. Why? Because the torsion has 3 indices, and the electromagnetic field has 2. But if you do field rate geometry, it is beautiful. When I obtained a result, I told a formidable mathematician, and he didn't need any more explanation. He said, oh yeah, he told me he had been working at that problem for many years. I tried this, I tried that, I tried that, I only tried one thing. Okay, so in that geometrization, one gets gravitational, I said, and Lorentz forces. What I'm saying, the Lorentz force is going to appear joined with the gravitational force. Yeah, geometrize Einstein's equation, you are going to say you are crazy. No, Cartan almost got it, but he didn't work at it. And the first pair of Maxwell's equations. Notice that the second pair is missing, because the second pair, the first pair only tells us that the electromagnetic field is not the thing. The important thing is the potential. So the second pair is not there. The first pair is simply what the first Bianchi identity with teleparallelism. You take only the linear forms and you get the first pair of Maxwell's equations. All right, but we learned something else also. That the indices that of the torsion that match the electromagnetic field, those indices are differential form indices. So the Dirac equation has to go to hell because it happens in the tangent bundle. It is about vectors in disguise, okay? It should be about differential forms. That means the Keller calculus. Probably you know what it is. Simply it is based on the Clifford algebra of differential forms. All right. So Keller, not Dirac. And this is a theory of a type, I mean, where the main animal is not a spinor. A spinor is an element of an idea. It is an element of the algebra. It can be decomposed, okay, into elements in the relevant ideals. But ab initio, the Keller equation is far more powerful, and there are some beautiful results. Exceptional. Okay. The type of Keller is the guy of the Cartan-Keller theory of stereo systems. He knew stereo systems better than anybody else. So instead of looking at the equation, look at what the solutions should be like. And the solutions, if you have, for instance, symmetry under time translations, you know that you have conservation of law and so on, conservation of energy momentum, and time translations on the conservation of energy. Where was I? Yeah, but the way any system of differential equations, whether partial or total, any system can be written as a so-called stereo system. And if the solutions with a certain symmetry not only give rise to the phase factors, that is because of the dependent on the coordinates but there is also, okay, an effect of how the solution has to depend on other typical differential forms, which give rise, to idempotents, which are going to generate ideas in the algebra of differential forms. When you take the two basic idempotents, are the ones for time translation and for rotational symmetry. And then the wave solution is decomposed, you can decompose into 4 pieces, which corresponds to electron positions, and the 2 chiralities of each, that is 4. The 4 are not, when I talk about 2 chiralities, think if you wish, the 2 degrees of freedom of spin, for a spin 1/2. All right. Was the green, right? Okay. Yeah. Then if you use that, okay, then you go, and together with these rotations from Clifford algebra, we go to the geometrization of quantum mechanics. Supposedly, I was going to ask you, but I think you are sufficiently interested. Okay, the Keller equation is something of this type. Do you see from the very end?
Yes. Yes.
Now, this is the wave function. This is an operator with the equivalent of it is the Dirac derivative operator. And this, it can be, but the Keller equation is far more general. This is a specialization which we use. We introduce the mass, for instance, when we solve for, when we develop the Hamiltonian from the Dirac equation. The Hamiltonian, I mean the Pauli Hamiltonian, and then the Folty-Watt-Quiescent Hamiltonian. But this is about the field. If you are talking about masses, you are already talking about the specialization of the field. And what happens is that you can decompose U, okay, into 4 pieces by virtue of the idempotents plus minus dx dy, and I forgot I. All right. What happens is this would be these 4 idempotents. Those 2 annul each other and those commute with those. So you would have here something like U plus, or let me call this epsilon plus minus, and tau plus minus. Anyway, I don't want to go into too much detail because I give detail if you ask for it. Now, we do rotations in a barbaric way. We still do rotations using coordinates and so on. When rotations are trivial, I can do them in half a minute in 3 dimensions, and in addition it is misleading. For that you use Clifford algebra. And in Clifford algebra, instead of, when you do rotations, instead of getting the unit imaginary, what you obtain is a bivector, E1, E2 in the exponent. So if you apply, replace here the bivector, okay, which would be E1, E2, and you use it here, this is related to rotations, then you get an element of a product of 2 algebras. The algebra of differential forms and the algebra of tangent vectors. And not only that, in the same way as you have dx dy, you could have dy dz and dz dx. If you replace them, I has gone away, and you have geometrized quantum mechanics by replacing the I and putting instead. Okay, geometrized in the sense that now you have geometric objects playing the role of the I. And there are 3 generations, except that he said, okay, it may look like that, but it cannot be because the animals from the 3 generations have very different masses. So there has to be a reason, okay, for that. And of course, there is a reason because, first of all, there is the dominant one, the dominant direction, which is the velocity with respect to the preferred frame. What preferred frame? I told you that with the special relativity, there are 3, with the Lorentz transformations, there are 3 options. One of them is a special relativity, and the other 2 options are consistent with the existence of a preferred frame. Anyway, the Keller theory has an advantage which, if Keller had written his theory the same year as Dirac, we would not know about Dirac. Because, for instance, the positrons appear automatically with the same energy as the electrons. So we don't need to think about the Dirac sea of infinite, an infinite sea of negative energy solutions and whole theory and all that. That is boring, it is not needed. Very good, the Dirac theory, we don't have anything else. But if we have something better, let's look at it. Not only that, we'll see that the Keller theory allows us, this is very important, allows us to change the foundations of quantum mechanics. Why? Because the probability, one of the tenets of quantum mechanics, I mean the Copenhagen school, one of the tenets, okay, the amplitude is an amplitude of probability amplitude. Well, what happens, that would mean that the continuity equation should be something partial rho with respect to t plus divergence of j equals 0. Conservation law, continuity equation. Well, what do you get with the Keller equation? This is fascinating. You don't get this. You get sub 1 plus partial rho 2 with respect to t plus divergence of g2 equals 0. And it happens that this is always not negative and this is always not positive. So we are talking about an animal which comes with two signs. So that is not a probability density, it is a charge density. The concept of probability density will be an emergent concept when you only have one type. Alright, so that was positive energy, rotation, geometrization, generations. So what happens? And when I geometrize the unit imaginary, that gives rise to the generations. And the fact, potentially, because it is not done yet, okay, is that now there are going to be three preferred directions. One is the direction with respect to the preferred frame, the most important one, and then there are going to be two, which will be, since particles are created in the accelerators, or directed by the accelerators, another one must set the direction of the gravitation, magnetic field, and the third one will be the perpendicular one. And that gives room, to explain, I haven't done it, as soon as I finish my summer. Okay, that is potentially, that might permit to, using a velocity with respect to the preferred frame, to explain the Kavigo, Kobayashi, Maskawa, Kavigo metrics. Okay? That's a good test. If it fails, forget everything. It's very beautiful. It goes far beyond what we know. In the ask me to talk about, I have a test. Ask me to talk about the geometrized Einstein's equations, about energy, gravitational energy momentum, localized. Okay? Ask me, but I want to complete this picture, if I may. And where are you? Okay. All right, the quarks. I'm going to jump because there is no time for everything, and I can't return to anything that you find of interest here. Leptons. Leptons for the electron are associated with, okay, there will be also for the gluon and for the tau, with 1/2 of 1 plus minus IDT, and here 1/2. But I said I was going to replace this with something. This vector is 0 in the tangent vector in the direction of time. It has a square minus 1, so it behaves like. And here is plus minus A1, A2, dx1, dx2. Okay. Now, in the same way as we have this, we have with, instead of x and y, we have with 1 and z, and etc. Here there is, as I said, the two positrons and the two electrons, the two chiralities. And spin and chirality here are very, very closely related. And in the same way, we have 3 more. Those are the 3 generations. So, let me go perhaps rather than quarks. So, the idempotents for the leptons are going to be epsilon plus minus, 1 plus minus. Instead of I now, I'm going to put AI, AJ, so I have dxi, dxj, so that I have now all 3 generations. I cannot go any further because I need idempotents that commute. And now, those take care of all the dependence. I mean, for the next set of idempotents, those which would have one more factor, that would have to be translations along the radial direction or translations along the z direction. But what happens? This is not possible because if I write the corresponding one, they don't commute with those. But I reach a product of 2 Clifford algebras. And there I get new idempotents, okay, a new set which commute with each other. And that is where quarks are going to be. So what form? I'm not paying attention now at the dependence on the coordinates, just on the idempotents that define the ideals into which you can decompose any solution of the Keller equation. Maybe I'll write what form they do take. I can save some paper. In addition to that, we'll have a third factor, which will be all the time 1 plus minus, and it will be dxi ai. But why are quarks not free? Because this has to be multiplied by a phase factor, and that phase factor is such that if there is a space translation symmetry, the probability density when we reach probabilities is going to be 0 at each point. So a quark is going to collapse as it is being born. I'll stop here because I want you to take something home, at least with regards to those things in which, okay?
About 7 minutes.
Yeah, all right, so whatever, I wanted to give people the opportunity to think that they have been bothering them. For instance, people are seeing problems when there is an opportunity. Q over M. Of course, if Q over M is related to the torsion, we are not going to consider the motion of that particle in its proper torsion field. Therefore, okay, there are lots of things like that. I mean, lots of beauty that I have not talking about. Okay, and details, I mean, why the radiation of free-falling particles, the form of the gravitational energy. You know what the, but for that I would have to explain a little bit about integral invariance. Okay, so I'll let you choose the topics I'm going to talk from now on in view of what I have already said. So please, questions. Yes, please.
Perhaps the central desiderata of science is to construct a theory that is, as the logicians call it, a logical system.
Yes.
Now, the formal logicians tell us that a logical system is comprised of primitive elements,
Yes.
Axioms,
Yes.
and then syllogisms. But they also tell us that there's no logical way
Yes.
to identify the primitive elements.
Okay.
You just think you have to intuit them or deduce them from empirical experience.
Let me ask you, we will continue.
Yeah.
Are you making an observation or are you...
Well, I'm setting up a question.
Yes.
My question is now, in your scheme of things, where do you put in the physical essential elements, the physical part, what is real, what is...
Okay, why is the word intelligible? So maybe when we describe, we have just to find on some grounds the mathematics that works.
Yeah. Okay?
I am sure that if I could do here with this, everything that has been done, you would not be asking more questions. Okay, because I mean, we don't know the reason, but I mean, everything works.
Yeah.
All right?
So, but still, what factors are the represent the physical thing? What can I take to the laboratory?
Oh, wonderful, wonderful, wonderful. Thank you. An affine space, okay, is defined by the affine group. In 4 dimensions, it has 10 what? Parameters. Okay? Although it has 10 parameters. If there no, but many more. 4 times 4, it has 20. But Euclidean connection, or what is known in the literature as metric compatible affine connection, there are 10 parameters. Which means that in a generalization of a Lorentzian space or Euclidean space of 4 dimensions, okay, there had to be 10 independent differential one forms. But we don't know the difference, we don't work at that level. Okay? We work at the level of curvature, torsion, and so on. Alright? So, what is the physics? As you know, we have the curvature, and probably you are satisfied with that with general relativity. I don't know whether you are or not, more or less. So let's assume teleparallelism. First of all, in teleparallelism there is torsion. If there is torsion, that means that the affine connection can be written as the sum of the Levi-Civita connection, not in the Rho connection, I mean the differential forms that represent it, plus something called the contortion. Then if we substitute, if we assume teleparallelism, I use that for curvature. That means that the affine curvature is 0 by hypothesis. Okay? And since this is the omega mu nu minus omega mu lambda, omega lambda nu, if I write this here and there, I obtain something very beautiful, which is the Riemannian curvature plus something which I'll write of this type, plus something which I'll write as the, okay, here I'm going to have d beta mu nu minus alpha mu nu minus, oh, it's like that, beta mu lambda, okay, what did I write here? Oh, I can present indices. Okay, there will be indices here, okay, I'm trying to make it brief. All right, this is a tensor-like. This is tensor-like. None of those is. That the sum of the 3 is. Now, this is more powerful than Einstein's equations, because Einstein's equations only speak of a contraction of this. But by the thesis of logical homogeneity, I'm going to identify these with the field equations. Which field equations? So from here, I can multiply this animal. It belongs to a tensor product of 2 algebras. Cartan already said, when referring to the curvature, that it is a bivector value differential 2 form. Not the 4 tensors. Tensors are garbage. Believe me, they lead to confusion, and if we contract this, the equation which Cartan gave to Einstein is very complicated, very long, and the different terms don't mean anything, even though you can write them in tensor form. Well, if you here, this is 2 vector value differential 2 form. If you have a tensor product of algebras, you are going to have a product here and a product there. This one for the differential 2 form, so that it, with an object which is a 1-1 object. So what you get, okay, with this product, one of those twos I talked about becomes a 1 index and the other one a 3 index. This is a value-net index. Why? Because it is the conservation law of, it is going to belong to time, first component of momentum, second and third component. In those three, it is because the energy, the curvature, the Einstein tensor, that tensor, I mean, that is nonsense. Nowadays, we should not talk about that. We should talk about the vector value differential free forms. Let me give you, this is the theory of differential invariance of Cartan. Instead of rho, if we integrate, we should write rho dx dy dz, or with other coordinates. But the current, how do we get the flow current? We replace, he gave the rule, not me, dx, replace it by dx minus ux dt. And if you do that, you are going to obtain the conservation law of a scalar value differential, of a scalar value quantity. Then, but in this case, in the case of energy momentum, since energy momentum is a vector, what we are going to have is vector value differential free forms. One obtains with this the generalization, with this operation, the generalization of Einstein's equations. And one of the terms, what happens is that we have been looking for energy momentum tensor. Einstein did, Latham did. When they didn't find anything, they said it's impossible, because there is no such concept as localized energy momentum in general relativity. That is not so. It simply happens that general relativity with the Left-Cheetah connection as a fine connection is incompetent for the task, which is a different story. I guess we'll have to leave this out.
If you want 9 more days of this, go to Brasov, Romania next week, and you can hear Jose is the star teacher for a summer school and a workshop. Thank you so much, Jose, for coming. All right, get on the bus, make the wheels go round and round.